All right, we're going to look at sections 3 and 4. They're about polynomials, kind of interpretations, graphing. First thing we'll look at is the power function. The book uses the power function of, they put a k, this thing right here, right? They will put k x to the p, where p is a real number and k is known as coefficients. What I like to do is I like to use it as just remove the k and just put xp as the power function, because then the k, we can go back to the transformation of functions. That's just either flips it or turns it over. Now, so one of the reasons, and even the book kind of does this, is they graph it with a 1 here, so you can see all the different ones. And they're looking at, in this graph right here, they're looking at x to an even power, and notice that the ends all point up. And so if your k was negative, then of course they'd all point down, right? So now if your p or your exponent is odd, then of course they go opposite directions, and in a case negative, it flips the other direction. Now, what is a polynomial? Polynomial function is just a linear combination of power functions, where this time the exponents are positive integers, right? This one said real numbers, but really they're only really talked about when they are integers is really kind of the key, because they're kind of moving into what is a polynomial. And so here the degree of the polynomial is the largest exponent of all of them. That's what we call the degree. And the lead coefficient is the coefficient on the term with the highest degree, and this is called the leading term. Now this tells us a lot about the polynomial, and we'll see that as we go along. If a polynomial function is in factored form, what would be a good first step in order to determine the degree of the function? Well, when you do that, the one thing you're going to have to do is talk about what a factor is and a zero, and there's a question coming up that brings that up, but also multiplicity, and that's how many times a factor or a zero occurs. So here's number 45 from the book, and notice that this one has two factors of x equals 3, because that's the 0, and x equals 2. Those are the zeros of the functions, but the factors are this x minus 3 and x minus 2. All right, and now how is that useful? Well, what we know is based on the multiplicity that if the multiplicity is 1, that it goes straight through. If it goes odd, they like to put in that there's a little curve in it like this, although how curvy it is you can't necessarily judge. It could come up and just kind of do that sort of thing. You got to be careful with how you draw it. So the one thing we know is that if it's odd, which these two are, you get crossings of the x-axis. Now if it's even, it comes and it bounces, just like a parabola. It comes down and it bounces off whichever way you're going. Now if we include that with the stuff about the degree, whether it's both ends pointing up just like the power function. Now why would that occur? Is because that dominates, and so then we can start telling a lot more about what the function is. So how do I tell the degree from a factored form? Well, the first thing you would do is you would look at whether these terms are linear, because what we know is that over the real numbers that it can either be factored to linear terms like these two, or this one, or irreducible quadratics like that. If we were in the complex, we could reduce this one even more, but in the real numbers we can't. So we have some things that can't be. Now, what we can do when they're just linear terms is we can just add up the exponents. So you can see that 3 plus 2 would give me a 5 for my degree on that one. This one, when it's an irreducible quadratic, then you would have to include the degree of whatever this one is. So this is 2 times 1 plus 2, so this would be a degree 4 polynomial. Where this one has the irreducible quadratic squared, so this would be 2 times 2, which is 4, plus 2, so this is a degree 6 polynomial. So you multiply these two together and then add it to, really, think of it like a 1. You're really just multiplying those two together. And really, you're doing that all the time. So this is 2 times 1 plus 1 times 2, which is 4. And this is 1 times 3 plus 1 times 2, which is 5. This is 2 times 2, which is 4. Now, that degree is going to tell us a lot of information about where the tails point, like we had back with the power function. In general, explain the end behavior of a power function with odd degree and lead coefficient. Well, let's do both. So if I have a power function, we already said this a little bit, is that if they're even, you can see that both the ends point in the same direction. Then if you throw in the coefficient being 0, or less than 0, then you get them pointing the other direction. If they're positive, they point the same direction. They point up, right? Both the ends go up. If your lead coefficient is negative, then they go down, like this. Because what does the lead coefficient do? It flips it over. Now, if it's positive and odd, you're going to get going down, and you're going to get going up, like that. And this one is just flipped when it's negative. So this goes up on this side and goes down on that side. Now, here's where this is some notation that's defining what we just said. This says, as I go to the left, my function is going up, right? And this one says, as I go to the right, in other words, positive infinity, I'm going up as well. So this goes, whether you go right or left, you go up. Now, same thing here. This is negative infinity, which is to the left. As I go to the left, I'm going down, negative infinity. As I go to the right, I'm also going down. So they're pointing the same direction. So if we come over here and look at this one, you can see that it says, as we go to the left, we're going down, which is what's happening. As I go to the left, my x's go to the left, my y's go down. Same with the other side, is if I go to the right, my y's go up, right? And here's the flip-flop. If your x goes to the left, that's what this says, negative infinity, right? And this is positive, so that means it's going up. As I go to the right, my y's go down. So that's exactly the same as what's happening with the power functions that we looked at before. If they're even, they go up. If they're odd, they go opposite directions, and then use the lead coefficient to tell which is which. What is the relationship between the degree of a polynomial function and the maximum number of turning points? So a turning point is where your graph goes from either increasing to decreasing, like this, or it goes from decreasing to increasing, right? So if you have something that looks like that, you'd have your turning points are these spots at the top and the bottom, like that. Now, what we can tell from that is that if I have a graph with 2 turning points, that would tell me that my degree of my polynomial is actually 1 bigger. So this would be at least a degree 3 polynomial because I have 1, 2 coefficients. But if I have a degree 5 polynomial, then I know it can have at most 4 turning points. So if I had a degree 5, I could have 1, 2, 3, 4, and then I would have something like that. 5's odd, so it flips a few times, and that's the most you could have, is 1 less. And that's what it's saying here, is that if your degree is n, you have n minus 1. What's the difference between the x-intercept and a 0 and a polynomial? Okay, so these are all kind of the same thing. An x-intercept is actually a coordinate on the graph, so it's an ordered pair. And a 0 is just where the function is equal to 0. So in other words, you say you solve the equation f of x equals 0, and those values that make this true, those are called zeros, right? And then, of course, if you factored the polynomial, you would get all the factors, and you set the factors equal to 0, and that gives you the zeros, like this, right? do that for a factor, it gives you the 0. Once you get the 0, you can write the intercept or vice versa. So they're all connected. So like in this graph right here, right, we have a 0 of -4, -2, 1, and 3. So I know that I have the x-intercept of -4, 0, -2, 0, 1, 0, and 3. I also know that I have the factors x minus a -4, which is x plus 4. I know I have x minus a -2, so that's x plus 2. I also know that I have x minus 1 and x minus 3. So I know I have those factors. Now the thing I don't know would be what is the multiplicity. That would be the thing that might change this. Okay, based on the look of this graph, it's probably just this, but they could all be squareds. We do know it has to be even though, so that would have to be part of it. Why do we know it's even? Because the ends, right, point both down. We know the lead coefficient is negative. We know that we know that it's an even degree polynomial from what we were just talking about. If a polynomial function of degree n has n distinct zeros, what do you know about the graph of the function? Well, we know that it's at least degree n, right? Because if you have 4 zeros like this, 1, 2, 3, 4, you know that it's at least a degree 4 polynomial. Now, it could be more because I don't know what the multiplicities are, right? Explain how the intermediate value theorem can assist finding the zeros of a function. Now, the intermediate value theorem says that if you have, if you take any two numbers, like if I said I take f1 and f2 and I have a continuous function, say f2 is this spot right here, what it says is that if I take any number between f of 1, which is this one, and f of 2, which is that one, if I take any number, there has to be something between 1 and 2 that gives me that value. Now, how is that useful? The way that's useful is that when you have a positive on one side and a negative, and you know the function is continuous, which polynomials are, then you know you have a 0. So what that tells us is that anytime we have an odd polynomial, because one side goes negative and one side goes positive, whether it's lead coefficient positive or negative, what that tells us is that somewhere in here has to cross the x-axis at least once, maybe more, but at a minimum of one time. And so the intermediate value theorem says would determine that every odd polynomial has to have one real 0, no matter what. Explain how the factored form of the polynomial helps when graphing. Well, okay, so we've kind of talked about this a bit already, right? We know that if I have x minus 3, I can pick out that this has zeros at 2 and 3. I can see that the degree is odd, 3 plus 2. I know that the lead coefficient, we'll talk about this, well, I'll know that it would be 1. Because if I took this one, x cubed and x squared, my lead coefficient is x to the 5th. Now, I could have a bunch of stuff in here when I multi it out, but I know that the last one is I would multiply -3, because the constant term, or the a0 term in a polynomial, is just plug in zeros. It's also the y-intercept. So I put to the 3, negative to the 2, right? So that would be -3 times 4, which is -12. So I know that it crosses way down here, which makes sense because this is degree 5, so I know that the tail behavior has to go something like this. And now, since this is a degree 2, what that tells me is that the behavior around it has to behave like a quadratic, a even degree polynomial, and this one has to go through it at degree 3. So I know that I get some graph that looks something like that it comes up from the bottom, hits this one, goes down, goes back up, and then goes through that one there at 3. And so all of a sudden I'm beginning to see what kind of polynomial I have. If a graph of a polynomial touches the x-axis and then changes direction, what can we what can we conclude about the factor of the polynomial? So, in other words, they're asking for something like this, right? I know then, just like I just said, that the multiplicity of this thing is at least 2. But more specifically, I know it's even. So it could be 2, 4, 6, 8, something like that. These, because it's kind of going straight through, I'm pretty much guaranteed there's no wiggle in it. It's probably, although I can't be 100% certain, but it's probably degree 1. So just by looking at this, I could guess that this would be like x plus 4 for that one, because it's probably degree 1, and I know this one is x plus 2, because that crosses through, and then this one would be x minus 3 squared, because I know it has to be at least. So that's the minimum this polynomial would look like, which is 1, 1, and 2, so that gives me a degree 4, which tells me it matches up with the direction that the ends are going. I know the lead coefficient is positive, so all of a sudden I'm starting to get a lot of information about the polynomial. All right, maximums and minimums. Now, anytime you have a turning point, we call those local maxes and mins, right? Because they're in a small region, they are the largest or the smallest value, like that. That's what we would mean by a local max and min. That in a small region around this point, that it is the largest, or in this case the smallest, the largest, the smallest. Now, global min would mean that it's the smallest value over the entire domain. So this one is a global min. These are turning points, right? So we have decreasing, increasing, decreasing, increasing. So decreasing means that if I put a little guy on this side of the function, and he's going to walk from left to right, he's going down is decreasing. So it decreases from minus infinity to whatever this x value is, and then increases from that value to that value, so that's increasing because it's going up, and then he goes down, and then he goes up. So it's on this interval from, let's see if I'm making a different color here, so negative infinity up to here, he's increasing, and then from decreasing. He's decreasing here, and then he's decreasing from right where he's at the top of the hill to right there. So he's decreasing in those green areas right there. Now if I put a blue in here, and then he's increasing between those regions there, like, and off to infinity like that. So you get that's where he's increasing from here to here. Oops, I didn't quite color it enough. And then go up to there. So here is a description. This is a global max because it's taller than anything. This is a local max because in a small region around the point, it's the largest one. This is a local min. There is no local min at all because they go down forever, so there's no smallest value. Just like in this one, there's no largest value. Alright, so this is a continuation, same stuff, just kind of put some notation in it. We can see that this is an even function because both ends are pointing up. Now, where's it increasing and decreasing? Well, if I put my little guy over here, right? And as he walks from left to right, if he's walking downhill, he's decreasing. So at minus infinity, because this is over the top of where he's walking, as he walks to negative 3, he reaches the bottom because he's going downhill in this spot right here. Now, from 0, we'll just assume that 0 looks like it's a little off, but that's okay. Up to 3, he's also walking downhill, right? So he's also decreasing there. So that's where we get negative infinity to negative 3 decreasing and 0 to 3. This term right here, this is union, but you can really just think of it as an or because that's the definition of union, in this set or in that set, or interval or, right, like that. Now, increasing, so we're at the bottom of this hill, we go up to the top, and so in this region right here, from minus 3 to 0, we get increasing. Now we're also increasing from here off to infinity because we're also going uphill at this spot here too. So we're going uphill here and uphill here. So from 3 to infinity, so we get that one. Now in this graph, we get minimums, right? These are both local, because in a small region around them, they are the smallest value, so they are local mins, right? And then this one is a local max, like that. But this one, because it's smaller than all other values, it's also a global min. And now because the n's go off to infinity, there's no spot where there is a largest value, so we know that there's no global max. What can we conclude if in general the graph of the function exhibits the following behavior as x goes to negative infinity, as x goes to positive infinity? So for polynomials, whether it's polynomials or power functions, really, when they have integer coefficients, if you go to negative infinity, right, and positive infinity, if both ends go up, we know the lead coefficient is positive, and we also know that the degree is even, right? If again, if we go to negative and positive, this is what we've said before, and you go down and then you up, so negative infinity and positive infinity, we know that it's an odd degree polynomial. Now if you multiply these, the lead coefficient by a negative, then of course by transformation stuff we know that it just flips to the other side, so now it's going to go down and down versus up and down. So it's just the opposite, which we've already talked about a few times. And so it's just reinforcing this idea of what is the tail behavior or the end behavior of this polynomial.